Hello everyone, welcome to the next lecture on properties of the uniform convergence. Today we will learn what is the relation between the uniform convergence and the Riemann integrable. Myself Dr. Harish Garg, you can follow my YouTube channel where you can find the playlist of real analysis. In this playlist you can see the various lectures related to the pointwise uniform convergence and many other lectures related to the properties of the uniform convergence. You must follow this playlist so that you can learn many easiest way. What is the objective of this lecture is if fn converges to the f uniformly and fn is my integrable function, can you say f is also integrable? That is the objective of this lecture. Once we will see this result is true or not, then we can try to explain this with the help of various examples. How you can evaluate this limit, how you can evaluate the limit and limit of the function and so on in this problem. So now we will see, as we have described these previous boundedness, continuity and differentiability in our previous lectures. Today we will see about the relationship between the uniform convergence and integrables. We all know if you have the two functions which are integrable, then the integration of f plus g is nothing but integration of f plus integration of g. And this result is also hold for the finite number of the functions. Now, can this result is extended to the infinite number of the functions? And that is the aim of this today's lecture. So what is the statement of that? If you have the sequence of the integrable function such that fn converges to the f uniformly, then the number one, you can say f is also integrable, and once f is integrable, you can integrate over the domain a comma b is converges to the integration of a comma b. Always remember student, always remember if fn converges to the f pointwise and fn is my integrable, fine, then this f may or may not be integrable. Fine, may not be integrable, but if it is a converges uniformly, then it's always integrable. The proof is a very simple. You can see what is given to you. F is my uniform convergent. So what is the definition of this? For a given epsilon greater than 0, there exists a positive number m such that fn minus f is less than epsilon. And if you taken as a x, then fnx minus fx is less than epsilon. Now your target is to find the value of the f. Can you find the value of the f from this case? It is fnx minus fx is less than epsilon. Now your target is to find the value of fn. So I can subtract fn on the both side, which is minus fx is less than epsilon minus fnx. Now can you find the value of the fx? I can multiply with a negative sign, so this inequality will change, then it is my fnx and this value will come as this side. So therefore fx will lies between fnx minus this. Another thing is also it is given that f is my Riemann integrable, or you can call as a Riemann integrable. What is the meaning of the Riemann integrable? There exists the partition. What is the definition of the Riemann integrable? There exists the partitions of the closed interval a comma b such that x1 less than x2 less than xn of the b, such that UPF of the function fn minus lower bound over the partitions of the function fn is less than of epsilon. Fine. Now we can start with this function f. Clearly say f is less than of the fn plus epsilon and f is greater than of the fn minus epsilon. What does it mean? If you multiply both sides by change of the length, then it will be fnx of the change of length plus epsilon into change of the length. And if you take the summation on the both side, what will happen? This is my UPF P of f. It is less than of U of P into Fn, because it is a supremum of this. And what is the supremum of epsilon plus n? or otherwise you can also consider this as supremum of the fx is less than of supremum of fnx plus epsilon. So this number is my UPF and this number is UPF with respect to the n. Similarly, for this case, because it's a lower bound, I can call as a LPF is greater than of LP corresponding to the n. Fine. Now, in order to show this is my integrable, your target is, what is your target? Your target is to prove UPF minus LPF is less than epsilon. So how you can find this value? Clearly say, if I subtract equation number 2 or 1 minus 2, so what will happen? This is less than of UPFN minus LPFN minus minus plus. So what is the value of this? Because f is my integrable, this is my less than epsilon plus 2 epsilon, which is equal to 3 epsilon. I called 3 epsilon is my epsilon dash. Hence, f is my integrable. Fine. And that's the proof of this first part. Look at the second part. What is your target? Your target is to prove integration of this. We can start from the f. Since fn converges to the f uniformly, it means fnx minus fx is less than of epsilon. Fine. I called epsilon over b minus a. Why I consider as a b minus a? I will tell you. What is your target? Your target is to prove this limit. That means converges. So that means your target is to prove fn minus of the a, it should be less than of epsilon. Fine. I can start from the left hand side. How you can write that? I can say it's a b over a fnx minus fx into dx. Fine. Now we all know integration of the f into dx is always be less than of the integration of the mod of fx. I can use the same quantity. It is less than or equal to b over a modulus of fnx minus fx. Fine. Now I can substitute the value of the fnx minus fx, which is less than of b epsilon over b minus a. Fine. So it will be, if you integrate them, it is b minus a into b minus a. That's why I have considered here is b minus a, so that it will be cancelled out. So therefore this limit is my epsilon and this limit is less than of epsilon. What does it mean? Integration of the a to b of fnx converges to the a to b fx. Fine. Or instead of this convergence, you can say the limit n approaches infinity is equal to of this case. Now, very important point is if fn converges to the f pointwise such that this limit is not true, then the function is not uniform convergent. So let's see, I can solve the 4 to 5 example in this lecture. I hope you can like, subscribe and comment on this video as well. Now, first of all, because we are talking about the uniform convergent, your target is to firstly check about the pointwise convergent. Now, when x is 0, second is x is non-zero. Fine. So in order to check about the pointwise convergent, what is your target? Your target is to compute limit of fn as n approaches infinity. For more detail about the pointwise convergent, I recommended you must watch about my lecture of example of the pointwise convergence. Now, when x is equal to 0, what is the value of the fn x? When x is equal to 0, the value is my 0. Therefore, fx limit as n approaches infinity of 0 is my 0. Fine. When x is my non-zero, then fx will be limit n approaches infinity nx e raised to power minus nx square. Now if you taken as a substitute limit, it is n is infinity, e raised to power minus infinity, infinity into 0, that is my indeterminate form. So that means we can convert into the 0 by 0 form or infinity by infinity form. I can write this number is e of nx square. Now clearly say this is my infinity over infinity form. Then I can apply the L'Hopital rule. I can differentiate this with respect to the n, e of nx square into x square. Now because x is my non-zero, so as n approaches infinity, this limit is my 0. So both the cases the limits are my 0. That means you can say fx is my 0 when x is 0 and fx is again 0 if x is non-zero. Therefore the sequence fn converges to the 0 pointwise. Fine. Now to check about this uniform convergent, the first way is you can apply the Mn test. Fine. You can apply the definition fnx minus fx less than epsilon. This is my method 1. Fine. This is my method 2. Fine. These two methods you can learn through my previous lectures, example of the uniform convergence and the Mn test, and that you can do it by yourself. Now I will explain you this, like how you can check the uniform convergence by using the Riemann integrations. So for that we need to compute limit interval is my 0 to 1 fx, limit 0 to 1 fnx. What is my f? F is my 0, so it is my 0. What is my fnx? Nx e raised to power minus nx square. How you can solve this? So clearly say if I take nx square is my y, then 2nx dx is my dy. I can multiply by 2 and divide it by 2. So this limit will be my half integration of y e raised to power minus, e raised to power minus y of y. But what is the limit? When x is 0, it's a 0. When x is 1, it is my n. Fine. So what is the answer of this? E raised to power minus y over minus 1 from 0 to n. I can substitute this value. It is my e raised to power minus n minus 1. Fine. Or you can substitute the value of the y is nx square. Now check whether limit n approaches infinity fnx into dx. What is the value of this as n approaches infinity? When n approaches infinity, this number is my 0, so the limit is my half, and it is not equal to 0 to 1 fx dx. So what does it mean? Therefore the sequence is not uniform convergent. Look at this another one. Consider the function fn. Find the value of the fx so that the function is my pointwise convergent. What is the definition of the pointwise convergent? Limit n approaches infinity fn x. So let's start with this fnx. Limit n approaches infinity nx plus 1 n plus nx square. So clearly say it is an infinity by infinity form. I can apply the L'Hopital rule. So it will be my x over 1 plus x square. If you take as n approaches infinity, this limit is my x plus x square. Fine. So therefore fnx converges to the my fx pointwise. Fine. Now how you can check about the uniform convergence? There are the two methods. Either you can apply the Mn test or you can watch about these examples of the uniform convergence. So I can use the Mn test. My target is to find the value of the fnx minus fx. What is my fnx? Fnx is nx plus 1 over n plus nx square. What is fx? Fx I have obtained as x divided by 1 plus x square. Now can you take the LCM? If you take the LCM, it will be, what is the LCM of this? Or you can write it as a separate. I can take nx over this, so that means x over 1 plus x square plus 1 over n plus nx square minus x over 1 plus x square. So this limit will be cancelled out. So the answer is 1 over n into 1 plus x square. Fine. Now because x square is my positive, modulus value is mine. So what is the value of this supremum of this quantity? 1 over n into 1 plus x square over the real line r. Now clearly say 1 over 1 plus x square is always less than 1. So therefore this number is always less than of the 1 over n. Fine. Clear? Or you can say what is the graph of the x square? What is the graph of the 1 plus x square? The graph of the 1 plus x square is x square is my this value. So at the point x is 0, this number is my 1. So I can take this limit is always less than 1. Hence mn is my less than 1 and it goes to the 0 as n approaches infinity. Therefore by using the mn test, sequence convergent uniform. Now evaluate this limit. There are the two methods. Fine. The first method is you can substitute the value of the fnx, nx plus 1 n plus nx square. Fine. And try to solve it. After the solving, take the limit as n approaches infinity. But the second method is quite easy and easily reachable because we all know fn converges to the f uniformly. Fine, that I have proved in the second part. So once it converges uniformly, then by using this today's lecture, that means, so you can see if this result hold, fine, from A to B and A to B. So I can use the same concept. So this will be nothing but limit f of x dx. So that is the quite easiest method. So what is the value of the fx? Fx we have obtained is x over. Fine. Now you can see the integration of this is much easier than the integration of nx plus 1. So what is the answer of this? Half log of 1 plus x square. So from 0 to 1. So if I substitute the value, answer is my half log of 2 is the answer of this limit. Look at one more example. Check whether find the value of the fx so that it converges pointwise. For again I recommended you for more detail about the pointwise and the uniform convergence, you watch my this playlist. You will be more confident after watching that. Again your target is to this. Again we can see I can write this limit is fx provided if I prove that fn converges to the f on the limit 2, 6.5. Fine. So anyhow, let's start with the first pointwise convergence. Now clearly say it is my infinity by infinity form. So I can apply the L'Hopital rule again. Limit as n approaches infinity, 1 divided by 2. So the answer is half. Therefore, fn converges to my f pointwise. Fine. Pointwise on the domain. What is my domain is R. Fine. Second part, does fn converges uniformly? Again I can start with the mn test. So what is the LCM? If you take the LCM, 2n will be cancelled out. It's a 2 sin x minus cos square x divided by 2 times 2n plus cos square x. Fine. Now we all know what is the value of a plus b. It is less than equal to a plus less than equal to b. So which is less than or equal to twice sin x plus cos square x divided by twice of 2n plus cos square x. Because the denominator is always positive, cos square is always positive, 2n is positive. Now what is that? Sin x is always less than 1. It's my 2 plus 1 3. 2n plus cos square, we all know 2n plus cos square x is always less than of the 2n. So I can say this is less than of 4. Fine. Now this is less than of 3 over 4n. Now as n approaches infinity, this limit will goes to the, or you can say this is my less than of 3 by 4n. and it goes to the 0 as n approaches infinity. So therefore, whenever mn goes to the 0 as n approaches infinity, by the mn test we can say the sequence of the f converges uniformly. Now once the sequence of the function f uniformly on the R, it also converges uniformly on the subset of the R. So what does it mean? That means limit n approaches infinity of fnx into dx, which is equal to fx into dx. Now the limit you can take as 0 to 6.5 or any other limit. So what is the value of the fx? Fx is I have obtained as a 1 over 2. So the answer is 4.5 over 2 is the right answer of the problem. Again, you can see about the last part. Again, Fn converges to the F uniformly. Then what is the limit? If Fn converges uniformly, what does it mean? I can say limit n approaches infinity, limit x approaches 2 of fnx. I can interchange its limit. X approaches 2, n approaches infinity. Fine. Now also, because fn is my continuous function, then by using the properties of the uniform continuous and convergence, we can say f is also continuous. Make sure, student, I can quickly recall that if fn converges to the f uniformly, fn is my continuous, then f is also continuous by the property of uniform convergence and continuity. Now once f is my continuous, fn is my continuous, we can interchange its limits. So what is the answer of this? Limit x approaches to, what is the value of this? This number is my fx, and what is the value of the fx? Fx we have obtained, the value is 1 over 2. So the right answer of the problem is half is the right answer. Look at one more example. I hope you can like and comment on this video as well. Again, your first target is to check about the pointwise convergent. How you can do that? Again, it's my infinity by infinity form. So limit n approaches infinity, 1 over 1 plus x square. So the limit is my 1 plus x square. Therefore, fn converges to the f pointwise on domain R. Does it converge uniformly? Again, we can start with the fnx minus fx. So what is fnx? X plus n divided by n plus n x square minus 1 over 1 plus x square. If you take the LCM, or you can separate them, you will get n into n plus x square. Fine. Now what is the modulus of this? Because the domain is my R, the numerator is always positive. Fine. But the numerator is my mod of x. Now I can substitute this value at this point. That means the supremum of collection of all those x over the domain R, mod of x divided by 1 plus x square into n. Fine. How you can find the supremum? There are the two methods. Because we are using the mn test, I can take an y is my 1 plus x square. Fine. Then I can start with the y dash is my 0. So I can say 1 plus x square into 1 minus 2x square is my 0. That means 1 minus x square is 0. So x is my plus minus 1. Fine. Then at the point of the 1, so x is equal to 1, we will get as the maximum point. How? We can take as the point of the 1. I can check about the sign of the y dash. So when y, because 0 is lies here, so whenever x is 0, it is my positive. Fine, and so on. Now, once we know y is maximum, this value is maximum at the x is equal to 1. So what does it mean? This implies this number is less than of 1 over 2 times n. Fine. So I can say mn is less than of 1 over 2n, and again it converges to the 0 as n approaches infinity. So by the mn test, the sequence converges uniform. How you can find that? Now again, because the sequence converges uniformly on the R, and 0 and 1 are the subset of the R. So therefore Fn converges to the F uniformly also on the closed interval. Therefore we can use this limit. So what is the value of the fx? Fx is my 1 plus x square. What is the integration of this side? Tan inverse x from 0 to 1. So pi over 4 is my right answer of this problem. This is the first method. Second method is you can substitute the value of the Fn at this point and then find the integrations and then take the limit as n approaches infinity. So that will take a lengthy, but whenever it's a uniform convergence, always use the properties. So I hope you can simply learn the concepts of the uniform convergence. This is the complete theory lectures of these sequences of the function available in my YouTube channel. We will start the next lecture on the infinite series, how you can check the uniform convergence of the series. Till then, you can like, share and comment on this video, and please don't forget to subscribe my YouTube channel. Best of luck students. Happy learning.